If direct substitution does not give an answer to a limit problem because an indeterminate form is obtained, usually 0 over 0, use algebraic techniques to change the form of the function inside the limit and then use direct substitution. Techniques that we've learned are factoring, combining fractions when you have a complex fraction, and rationalizing the numerator or denominator when you have a rational function with a radical in it. So let's begin. The limit as x approaches 0. If I direct substituted 0, you would notice you'd get 0 over 0, which is indeterminate, absolutely not an answer, not allowed, doesn't mean anything mathematically. So we need to reduce. X over x is actually 1. So this is the equivalent function, or the reduced function is 1 over x plus 1. Now, can I direct substitute 0? Yes, I can. When you direct substitute, you do not write the limit notation any longer. Here we have a rational function with polynomials in the top and bottom. Perhaps we could factor. Oh, the denominator is difference of perfect squares. So that will reduce. In our reduced function, we can plug in 2, and we get the value of 1/4. X cubed minus 1, that is difference of perfect cubes. Do you remember how that factors? You better, because it's going to pop up on a quiz. All right, there's our form, so let's factor. X minus 1, x squared plus x plus 1. The x minus 1s will reduce to be 1. Now we can direct substitute. And there's our limit. All right, here I have a radical in a rational function. And so rationalizing the numerator or denominator was the technique for that. Our radical is in the numerator, so we're going to rationalize the numerator by multiplying the numerator and the denominator by the conjugate of the piece that has the radical, of course. This is just multiplying our function by a special form of the number 1. When you multiply by a conjugate, those middle terms will reduce to 0. So root x squared and then minus 1 squared. That is simply x minus 1 over x minus 1 times root x plus 1. X minus 1 over x minus 1 does reduce. And now it's time to direct substitute. When you have a complex fraction, our technique is to combine those fractions. So let's get these to have the same denominator. I'll need to multiply this one by 2 over 2, a special form of the number 1, and this one by x minus 2 over x minus 2. Yay! Now I can combine those fractions in the numerator. A fraction divided by x would be the same as this fraction times 1 over x times the reciprocal. And oh, x over x is 1. Now I can direct substitute. And there's our limit. Discuss the continuity of f of x. This is a piecewise function that doesn't have like a left-handed piece and a right-handed piece. This is a function For all x's, it's defined as this rational function, and then for this one value of x, it's defined as 5. So we know that x minus 3, x can't equal 3 because that would make the denominator equal to 0, but I would like to know what the behavior of this rational function is at 3. Is it a vertical asymptote or is it a whole? So I'm going to factor the first piece, x minus 3 plus 1. All right, x minus 3 over x minus 3 does reduce, so we know that 3, x equals 3, is a whole, not a vertical asymptote. This means that this entire function is just a line, but not at x equals 3, because at x equals 3, the y value is 5. Graphically, this is what we have. So to discuss the continuity, x equals 3 is a whole, a removable discontinuity. For number 8, if g of x is continuous, then find the value of a. In order for this to be continuous, our left-handed limit needs to match our right-handed limit. The limit as x approaches 2 from the left of g of x. That would be the second piece, the piece without our unknown, and I'll plug in 2. The limit as x approaches 2 from the left of g of x has to equal the limit as x approaches 2 from the right of g of x in order for this function to be continuous. The limit as x approaches 2 from the right of g of x needs to equal -1. If we're approaching 2 from the right, then we're going to use this first piece to direct substitute. 3 times 2 squared plus a, and that still needs to equal -1. Now you have an equation you can solve. And a equals -13 in order for us to have a continuous function. Our calculators don't actually have a limit evaluation, so what we're going to do is we're going to plug in this function for y1 and then look at what the table tells us. So first, type in this function for y1. It's also the same one as over here, so we won't have to retype it. Once this function is your y1, we want to look at the table and see what is happening to the left and the right of x equals 1. In order to look at the table, you could press second graph, which gives you the table, but the table is changing by integers, so we want a little bit more of a precise, a little more exact valuation. So we're going to go to table set, which sets up how we want the table to look. That's second window. When you do table set, it's going to ask you what you want to start at, your starting value. I'd say let's start at 1 because that's what we want to find the limit around. When it says delta table or triangle table, that's asking how much do you want each value in the table to change by. And I want it to change by 0.001, not by integers. I want it to give me all those decimals. Now that you're done setting up how you want your table to look, go back to the table. So I scrolled up a little to see what was happening to the left of 1, and then I can see what's happening to the right of 1. I noticed that as we're approaching 1 from the left, we're getting just massive numbers. It looks like it's approaching infinity. And as we're approaching 1 from the right, it looks like we're headed down toward negative infinity. So yeah, the left side and the right side limits do not match up. Therefore, this limit does not exist. To evaluate it when the limit is 2, let's go back to the table setup because you don't want to have to scroll through to get to 2. And start at 2. Now go back to the table. Scroll up a little to see what's happening to the left and right of 2. And when you plug in 1.999, your y value is 0.33278. When you plug in 2.001, your y value is 0.33389. Let's adjust our table setup one more time and change the change in the table to 0.0001 to get a little bit more precise. All right, when we do that, that's going to round with 3 decimal places, since that's what we do for AP Cal. We're going to round that to 0.333. All right, the intermediate value theorem. When we use theorems in AP Calculus, we have to establish the conditions in order to use that theorem. You have to write out that the conditions have been met before using that theorem. And what are the conditions? That would be f is continuous on the closed interval a to b. Absolutely necessary. So not only do you have to look at it and say, okay, yeah, f is continuous, you have to write the words f is continuous on the closed interval a to b in order to get full credit in AP Calculus. If f is continuous from a to b, the closed interval, and k is any value between f of a and f of b, then there is at least one x value c between a and b, such that f of c is equal to k. You have a y value in between other known y values. There will be some x that satisfies that y because it's a continuous function. So does the intermediate value theorem guarantee a c value on the given interval? What we're going to do to test it out is, first of all, we're going to establish if we are continuous. This is a quadratic and all polynomials are continuous. So write f is continuous on 0 to 5, the interval we're looking at. All right, so we're going to plug in 0 and plug in 5 to see if 12 is a y value between those. All right, the y values are 0 and 20. So this is basically asking us, is 12 between 0 and 20? Yes, it is. So yes, our reasoning is that 12 is between f of 0 and f of 5. And then we'll solve for that c value in part C. Here I have a at 2, and that's on our interval. If it wasn't on our interval, then that's fine, but it's not continuous on the interval a to b. So f is not continuous on 0, 3. To find the c value, we want to know what is the x value that makes our y value 12. I'm going to set f of x equal to 12 and solve. This is a quadratic, so I'm going to make everything equal to 0 and factor. The two x values that satisfy f of c equals 12 are -3 and 4. But remember, we have an interval. We're only asking for the x value that's on the interval. For this one, only one of them satisfies this interval. Therefore, c has to be 4. Cannot be -3